Good afternoon, dear colleagues. My name is Valerii Dymo, and I want to present our research paper's topic, Application of Convolutional Neural Networks for Detection of Damaged Buildings, by authors Aleksandr Gozhyj, Irina Kalinina, and Valerii Dymo, Petromohila Black Sea National University. The introduction. Natural disasters, hurricanes, earthquakes, tsunamis, and factors directly caused by human activity, like hostilities and wars, bring enormous destruction, cause direct and indirect damage to the economies of the countries. In such cases, their task is to determine the scale of destruction, critical areas in which there is greatest need to provide assistance to the population, drawing up a recovery plan, in a timely manner and in the necessary volume. Convolutional neural networks are able to determine various patterns in the complex images, and modern architecture could be more accurate than classical algorithms. It is difficult to obtain high-quality photos from the places of hostilities, so there is a need to use different approaches to increase the variability of the existing dataset. For example, use data augmentation methods or optimization of the neural network's architecture itself for working with a small number of images. A combination of different approaches will improve recognition performances. The key to solving problems is finding the tools and approach. So the purpose of this paper is to study convolutional neural networks for solving the problem of detection of damaged buildings, building an application of a convolutional neural model for detection of damaged buildings on satellite images. As you can see, the ways to solve the problem are follows. First, application of modern technologies for obtaining information like satellite images or using drones. Second, application of artificial intelligence and computer vision algorithms for image processing and analysis. And the last, integration of implemented components into a single intelligent system. The next slide presents techniques and networks for solving the problem. So each technique entails the need to use certain approaches and appropriate models. In the figure on the right, you can see a comparison of different computer vision techniques. The authors suggest using the semantic segmentation technique, in which each pixel of the image is associated with one of the classes. This will allow more accurate classification of damaged buildings, generating segmentation maps of affected areas, and the results of which will be easier to interpret. Today there are a large number of models of different convolutional neural networks. Each architecture has its own advantage in some tests. For example, the VGG model shows high accuracy in classification tests. RCNN network has been applied to object detection tests for various data sets. Modifications such as faster RCNN or mask RCNN can be used to solve object search tasks in real time and image segmentation. Let's talk about U-Net convolutional network architecture. As the selected model, the U-Net convolutional network is proposed, which is based on the idea of a fully convolutional neural network, which is effective for capturing both context and spatial information. Here is a U-Net architecture in the figure on the left. In general, this architecture is similar to encoder-decoder model, has fewer parameters due to lack of fully connected layers, but compensates for this with a greater complexity of expanding path. Summarizing the work of the model, the structure of the network can be divided into several logical blocks. The first is convolutional block. It consists of a 3x3 convolutional layer and ReLU activation function that are repeated twice. Encoder block is a contracting path block consisting of one convolutional block and pooling layer. The bottleneck is the narrowest part of the model, consisting of a convolutional block with a maximum multiplier of filters, and the last is the coder block, is analog of encoder block for expanding path, which consists of an upsampler layer and a combination with a corresponding layer from a contracting path, dropout layer, and corresponding convolutional block. This slide provides brief information about the dataset used. In this paper, the authors use their own dataset created using satellite images from the Google Earth service. The dataset has a small amount of data, only 50 satellite images with a size of 512, which contains images of buildings from the private sector of the city of Mariupol. The pictures were taken in May 2022. And at the same time, the dataset contains more than 1,500 instances of different buildings which belong to two classes, damaged and undamaged. The figure below shows an example of images from the dataset. The next slide is pre-processing. Thus, in total, the dataset contains 100 images, 50 sources images to be used to train the model, and 50 generation segmentation maps for them, each pixel corresponding to one of the three classes. In the figure on the left, you can see the original image, the processed image, and its segmentation mask. Since the initial data set has a small number of images, the author decided to apply data augmentation, expanding the set by adding images already existing in the set with certain changes. For example, the figure on the left shows several augmentations. It is worth noting that the large amount of image manipulation can lead to loss quality and clarity, which will affect the learning of the neural network. That is why various combinations of defined augmentation with limit values for geometric transformation are used in the work. For example, image shift, scale, rotation, and blur. Several functions and metrics are applied in this research. For example, the softmax function or normalized exponential function transforms a vector of real numbers into a probability distribution of possible outcomes. The second one is categorical cross-entropy, is used as a cost function, which is common in solving semantic segmentation problems, which measures the distance between the predicted distribution and the actual distribution of classes. Also were used two different metrics. Intersection over union is a popular metric used in machine learning to measure localization accuracy, calculating localization error in different models. As mean intersection over union, which reflects the average value of intersection over union for all three classes, while common intersection over union will be used to calculate the indicator separately for building classes. This slide contains comparative analysis of models with different parameters. As part of the experiment, an initial model was built. The initial value of the filters was 32, the input image was 256 pixels, and the dataset was increased by 10 times. The dataset was split into training and test sets in the ratio of 80% to 20. So the model was trained on total of 400 images for 25 epochs. On the slide you can see some of the results of the model in the figure on the right. So, since the model was trained on a small dataset and dropout layers were applied, the image has typical teeth. The overall accuracy of the initial model is 82.28%, but this does not indicate its accuracy with respect to the main classes damaged buildings. So, comparing the intersection over union scores for each class, the results are follows. 42.67% accuracy for damaged buildings and 38.37% accuracy for undamaged buildings at the pixel level. This slide shows the effectiveness results of the models on the test dataset. The table contains models and corresponding indicators for each of them. 5 models were built, including the base model, which had different parameters. The size of the image could have a positive effect on the quality of the model, but the increase to the original size was not possible for technical reasons. Based on the obtained results, it was possible to improve the overall accuracy of the first model to 84.21% respectively, and the recognition of damaged buildings at the level of 45.28% 83% and undamaged and at 49.20%. The conclusions are 5 different models of the UNet architecture were built. The influence of various parameters on the effectiveness of the models was investigated. According to the results, the initial numbers of filters has a positive effect on the accuracy of the model. In turn, there is no need to train the model on the large number of epochs, since in most cases this leads to overfitting, which can be avoided in case of increasing the datasets with original images. So, a segmentation accuracy for damaged and undamaged buildings was increased. Thus, the application of convolutional neural networks of the UNet architecture allows recognition of general features of damaged buildings in images, and the proposed approaches makes it possible to make a preliminary assessment of the damage of damaged buildings and contributes to the implementation of recognition systems based on convolutional neural networks for solving such practical problems. The presentation is over. Thank you all for your attention.